Okay, let's start today's class. And then please check your attendance on Blackboard. So in the previous class, we learned about the data path elements in the RISC-V single-site processing. Right. So what are data path elements? So you can think that data path elements are so the input data is given to these elements, and then the output data are generated. So which means that if a certain component generate data using the input data, then you can say that these components are data path elements, right? So, okay. So we learned about some several data path elements in a single cycle RISC-V processor, so such as the registers, ALUs, and then memory. It includes instruction memory and data memory, right? And then some multiplexers. Okay. So I will explain about the course lab assignment. So even though the deadline of the lab 3 is a Friday, but I posted this course lab design lab. Okay, so actually in this design lab, the first design lab, so you are requested to design data path elements, right? So if you read the lab document, then you can find that you need to design 4 data path elements. Those are instruction memory, register file, data memory, and ALU, so arithmetic logic unit. So I will briefly about each data path element. Okay, so we already learned about the data path element. Okay, and then so firstly, so you need to design instruction memory. So if you see this instruction memory, you can find that the instruction memory has 2 ports. So one input port and then one output port. And then actually I explained that in the memory, if the address is given, then the data of the corresponding address is generated. So it becomes the output of the instruction memory. So as you can see, instruction memory has 2 ports, the read address port and the instruction port. So actually this instruction is the data. Okay, the data. So you can see the some skeleton code of the provide system payload. So actually for this lab, I provided some skeleton system payload module for each data path element. So each module, actually for each module, so input and output ports are actually defined. So if you see this IMEM, so IMEM represents the instruction memory. So you can find the module name here, IMEM. So and then you can also find the 2 ports. So one input port and one output port. So input port is the address, and then output port is the out, right? Actually, this is the data out, okay? Because the data is out from this port, so it is called the out. Okay. So and then the width is given here. The IMEM address width is 10. It means that it's 10 bit. The address is 10 bit. So even though actually in the RISC-V processor, I mentioned that actually the PC is 32 bit. Okay, but so actually this IMEM size is small. So instruction memory size is small. So we only use the 10 bits of address. Okay. So this is 10 bit, and then so the width of data out, the width of instruction is it's a 32-bit, right? So it's the same to the size of a single RISC-V instruction. So you can design the instruction memory, like so its address is given, then what is the output? I said that in the memory there are many elements, and then we can think that a memory is an array, right? So one of the array will become the output of instruction memory by this address, because we can use this address as an index of data array in the memory, right? So think like this. Data, then address. Okay. So this will be output of the instruction memory. It's very simple actually. Also, I also provide the test bench for each data test element, so you don't need to design a test bench for this lab. So actually, you need to design this module only. But you know, the instruction memory is very simple, right? Right. Okay, how about the register file? So this is the next data test element. And then, as I explained, the register file has 4 input ports actually, and then actually 3 register number input, and then 1 data input. This is the data input, it's the right data. This is the data input, okay? And then read register 1 and read register 2, and then write register is the register number inputs. Okay, so this is the RS1, this is RS2, and then it's the RD. And then register file has 2 output ports, the read data 1 and read data 2, because so we use RS1 and RS2 as indexes of this read data 1 and then read data 2, right? So which means that if the RS1 and RS2 are given to this register file, then we can read the stored data in the register file, right? So this is the I don't know so we can find that this is the RS1 D out. This is the RS2 D out. Okay. So I also provide the skeleton code of register file. So, and then nobody. Okay, so you can find the input and output ports of the register file. Then the RS1. This is you can find the comments here. The source register 1 is the source read register 1, the RS1, the RS2, and the RD. And then also another input is write data. This is the RD underbar T in, because I said that this is the data input, so we frequently use the T in. So it's the data input. So this data input is for RD register, right? So that's why I named this port as RD underbar T in. Also, this register file has a control bit, a control signal called read write. Okay, you can find the read write here. So this is the control signal. So which means that if read write is 1, if read write is 1, then write is enabled. Okay, so this is so we use the read write port for is proposed. Also, as I mentioned, the register file has 2 output ports, RS1 D out and RS2 D out. Okay. And then register width. So it's a width of it is the width of the single register. Okay. So width is defined as 32. It's because it's a 32-bit computer, right? So it's actually this port, the port list of this skeleton code is identical to this figure, except black. So actually, unlike this figure, so I provide the register file module that includes clock signal. So which means that the register, this register is working with the clock signal. So actually, this is the same file. So I also kindly wrote some comments for each operation. Okay. So you can find the array of register file here, the RF underbar data. As you can see, its single register file is it's defined as the leg read, and then there are 32 registers, right? And then you need to define write operation here, and then you need to define read operation here, right? And then actually the read operation is very simple. So it is because we can read the data indexed by RS1 and RS2, right? So this is the array, the RF data array, and then we can just read the one of array elements indexed by RS1 and RS2, right? But you need to think about the zero register. So it is because in the RISC-V, zero register has always zero value, right? What is the zero register? It's X0, right? So it means if the register number is 0, then output of is RS1, output of the out. The output of this register needs to be 0, right? So for example, if RS1 equal 0, then okay. So you need to consider the 0 register, okay, for the read operation. Then how about the write? So you can find that actually the clock signal is used for synchronizing write operation. So why? So actually you cannot find any clock port here, but actually when the hardware is designed, the register file hardware is designed, the write operation needs to be synchronized by clock signal, which means that the write operation is to be performed at the rising edge of clock. Okay. Also, you need to consider the reg write signal. Okay, this is the write enable signal. Okay, so you need to actually, this is the flip-flop read. It's similar to the flip-flop read enable signal. Okay, because we use the reg write as the enable signal. Then why do we use clock? Why do you use clock signal for write? Think like this. So add x1, x1, x1. Actually, this instruction is possible, right? So and then let us assume that x1 has 1. Okay. Then what is the value of x1 after this instruction is executed? So obviously 2, all right? Because so it's 1, and then it's 2. So actually, this instruction means that so we read data from register x1 and x1, and then also the update value is stored in x1. Okay, then what is the problem? So it looks like this. So it's an x1 and then x1, and then we perform add operation, and then actually this data is updated to x1. Okay, this is the feedback loop. So actually, so if we do not use clock signal here, then this value is added, updated again and again. Okay, because you can find that this is the loop, right? Do you understand? So x1 value are added together, and then new values are updated. And then if the x1 is updated, then we need to recalculate this operation, right? Because this is loop, okay? So in order to avoid this situation, the right operation is actually synchronized by clock signal, okay? So which means this is the single cycle processor. So which means that the every operation, every instruction is complete within a clock period or clock cycle. Okay. So then actually the write operation is updated to the register file, the very end of this clock cycle. Okay. So that's why we need to use the clock for the write operation. So it's the same for the actually data memory. Okay. So we need to avoid this situation. Okay. And data memory. Okay. So the data memory has two input ports and then two control inputs. It's a memory write and memory read, and then one output port. So this is the read data. So this is the actually D out, so data out, and then this is D in, and then this is address, right? And then as you can see, the data memory has the two control signals, the mem write and mem read. Also, you can find the port list here. The port list of is data memory module, and then also you can find the clock here. So it's the same reason. Okay, so actually the data memory also has the write operation. The write operation needs to be performed at the end of the clock cycle. Okay, in order to avoid the infinite loop. Okay, like the add x1, x1, x1. Okay. So as you can see, so it's very similar to the register file, but I mentioned that actually the register file is the structure of the register file is similar to the memory, but the memory size is larger than the register file. And then we use the register number as the index of these registers, but we use the address input as the index of the memory. Okay. So as you can see, the write operation needs to be synchronized using clock signal. It's the same reason. So it's the same to the register file. Okay. And then the read operation is also similar, but we have actually the data memory has the mem read control signal. So this is the behavior of the data out for the memory read control signal. Okay. So if mem read is equal to 0, then E out becomes 0. Okay. So you can implement this one. Okay. So it's a write operation, the read operation. Also, write operation is enabled if mem write equal 1. Okay. The write operation is also enabled only if mem write is equal to 1. Okay. So this is also very similar to the if flip-flop with enable signal. Okay, this is the data memory. Then the final data path element is the ALU. Okay, so actually we will learn about the ALU in this today's class. Then the you can think that ALU is the function of ALU. It looks like the y equal f and a comma b. So a and b are input data of ALU. Then y is the output. But we can select the function of ALU using ALU control signal, like the ALU control. So based on the ALU control signal, the ALU can perform add operation. So it's the same. ALU control signal is the same. Add operation and then sub and or exclusive one. So based on the ALU control signal. So actually the operation is changed, but data are the input data is the same. Input data are the same. And then the output is generated based on the defined function. So and then this function is defined by ALU control signal. Okay. Then so let us so actually in the textbook, our RISC-V processor just supports the small number of instructions, but I added the more instructions for this design lab. So actually, this ALU needs to support the load word and then store word, then branch it, the BQ branch instruction like BQ, and then BNE, BLT, and BGE. And then also need to support the R-type and I-type arithmetic and logic instruction. Okay. But actually, so this we can define the ALU control signal using OP code field. Okay. So load word has store word and branch has the different OP code field, and then for the R type and I type instruction like the add and add I. So for the R type arithmetic and logic instruction, the OP code field is the 0110011, and then for the I type instruction, I type arithmetic or logic instruction, and the OP code field is the 0010011. So based on this OP code field, then we can define the ALU OP actually. So this is the control signal for the ALU control generation. Okay, and then the specific function of ALU is defined by actually function 3 or function 7 field. Okay, so but actually just ignore this control signal, because if you see this ALU module, so you can find that ALU receives the two input data like A, B, and then it generates the ALU result, like the result is the F and then A, B. Okay, and then this F is controlled by ALU control and ALU control. So you can find that this is the 4-bit signal. Okay, 4-bit control signal. And then this ALU also generates the 0. Okay, which means that if results equal 0, then it becomes 1. Okay, it indicates that the result is 0. So generated result is 0. Okay, then it becomes 1. Also, I added another port called the sign. So it represents the sign bit of result. Okay, so which means that if the result is negative number, it's a negative number, then sign becomes 1. Okay, do you understand? So actually, it's the sign bit of the result. So actually, we require this signal to support other branch instructions like the BLT or BGE. Okay. So this is the this is the port list of the ALU. Okay. So as you can see, this port list is identical to this figure. Okay. So ALU receive two input data, and then the width is 32 bit. Okay, and then ALU control is the 4-bit control signal. So as you can see, you can find the ALU control signal here. And then, as I mentioned, based on the ALU control signal, the ALU function is defined. So for example, if the ALU control is 0010, then ALU will perform add operation. Then 0110, then it will perform sub instruction. 000 and 0001. And then result is just the result. Okay, the result of the defined function, and then 0 and sign. Okay, so this is the ALU. So you can use case statement to design the ALU. Okay, you can use the case statement, and then input of the output is changed by output is defined by ALU control signal. So you can define like the case ALU control. Okay, and then you can define output result of the ALU based on the ALU control signal. Okay. So this is the end of the slide for the course lab assignment. And then, so as I mentioned in the lab assignment document, so you need to learn how to design the RISC-V processor hardware. And then the best way to understand the hardware architecture is to design the hardware by yourself, right? That's why I just provide the design lab assignments. Okay. Then this is the second step. So in the first step, the first lab, so you are requested to install CAD tool, right? So it's very later. And then in the second lab, you are requested to design data path elements. That was the third step. So single-sided processor. And then the fourth step, pipeline process. Okay. So any question about the lab? Okay. So I also recommend you start early. Okay. So I hope everyone can complete the course lab assignment. Okay, so I believe I explained about this course lab assignment, but I believe I also believe that I already reviewed what we learned in the previous class, right? Because I explained about the data path elements in RISC-V. Okay. So, and then I explained that is the full data path of the RISC-V. So actually, so firstly we define each data path element, okay, like the instruction memory and then piece register and then register file, data memory and ALU. And then we can just you can find some flow. So how the data is transferred from one element to the other element. Okay, so you can find some flow of data in this figure. So this line, okay, so this black line represents the data flow. So that means that path, path where data is transferred. Data are transferred from one element to other element. Okay, so you can think that, oh, this using this black line, through this black line, the data is transferred. Okay, it's generated by a certain component, then the generated data are given to the other components. So by connecting input and output ports of data path element, we can define the full data path of the RISC-V, right? So we just connect each component, and then we can build the full data path. And then how about this blue port, blue line? These are control signals, right? So what are control signals? The control signals determine the operation mode of data path, right? So for example, so think about the read write. If the read write is 1, then this register file write data. Okay, so which means that the data is updated. But if the read write is 0, then the data is not updated. So control signal determine the operation mode of data path element. So actually, we can make the full data path here. Also, we need to define control signal in the RISC-V process. Okay. So we need to define control unit. So which means that this control unit needs to generate the control signals. Okay. So what are control signals? As I mentioned, you regulate here the ALU operation. So it's the ALU function operation. And then also you can find the mem read, mem write, and then some other control signals here. Also, our full data path, so the single cycle RISC-V processor has multiplexers. Okay, so here and here and here. So and then each multiplexer has select signal, right? Which means that the output of multiplexer is determined by selection signals like I0 and I1 by selection signal. So these selection signals are also control signals. So the control signals needs to define every control signal connected to data path element. Okay. Then how can we generate the control signals? So if you see this figure, what is the input of a control unit here? The input is instruction. Actually the output of instruction memory. So and then we already know that the output of instruction memory is instruction, right? Instruction. It's the 31 down to 0. So based on the instruction, we can generate the control signals. Okay. So how? So okay, let's see this slide. So we firstly you think about the control signal here. Okay. So actually this is the full data path with the control unit. Okay. So like this figure, but this figure is slightly different. So why? So there are two control units. The main control unit is here, and then you can find the ALU control unit. Okay, and then also you can find some control signals here. These are the output signals of control unit, the main control unit. Okay. Also, what is the input? The input is instruction 6, bit number 6 down to 0. So what is this actually? This is the OP code field, right? Right. This is the OP code field. Okay. So what is the OP code? You can find the OP code in here, and then OP code defines the classes of instructions. So for example, this is the OP code of load instructions, and then this is the OP code of store instruction. And then for the arithmetic and logic instruction, like the shift, arithmetic, logical, and compare. So there are two types of OP code. So OP code for R-type instruction, then OP code for I-type instruction for shift, arithmetic, and logical, and compare. Okay, you can find the OP code here. And then branch. Branch has also different OP code. Then jump has the also different OP code. Okay, here. So actually, if this is the OP code field, if we see the OP code field, then we can know the class of instruction. Okay. Then how can it define the control signal? We can define control signal based on the operation of required operation of instruction. Okay. So how about the add? So let's see the example. Okay. Oh, here. So let's see the example like the add x1, x2, x3. Okay. This is the R-type arithmetic instruction. Okay. So we can define the operation of this instruction, right? What is the operation? Read two source operands from register file, and then these two source operands are transferred to delivered to the ALU, right? And the result, ALU result is written back. So ALU result is written back to the register file. Okay, so this is the required operation of this R-type arithmetic instructions, right? Then how can you define the control signal? So actually branch is 0 because it's R-type arithmetic. It's not a branch instruction, right? So it becomes 0. So the output of this AND gate becomes also 0. So which means that PC plus 4. So next PC is the PC plus 4 because this is the R-type arithmetic instruction. Okay, so branch is 0. How about the mem read? So if the mem read equal 1, mem is equal to 1, then the memory is accessed. The data memory is accessed. But you know, the add instruction does not access data memory. So mem read is 0. Obviously, right? How about the mem2 reg? So where is the mem2 reg? So mem2 reg is connected to this multiplexer, and then this multiplexer selects the data input. Data input for this register file, right? So one of input comes from ALU, right? So this line this line. And then another input comes from memory. But this is the R-type arithmetic instruction. So we need to use the ALU result. Right. So we need to select this path. Okay, that memory. Then you can find that if the selection signal is 0, then its path is selected. Okay, so which means this is also 0. Map to regular. So map to regular is also 0. And then we will skip the ALU operation. So we will learn about the ALU operation later. Then, but we can also select the ALU operation based on the OP code. Okay. How about the map right? Oh, this is not a store instruction. So map right is also 0, right? ALU, so how about the ALU source? So ALU source is connected to this multiplexer, right? And then this multiplexer is size register 2 is given to the ALU, or then immediate number is connected to the ALU. Okay, but this is the R-type instruction, right? So ALU needs to receive RS2 data. So which means this path needs to be selected. Then, as you can see, if you see that this is multiplexer, then you can find that, oh, if this selection signal is 0, then this path is selected, right? So what is the ALU source? ALU source is 0. How about the regular write? Regular write is 1 because this R-type instruction stores updated results to destination register. So register write is required. So regular write is 1. So we can define control signals based on the required operation of each instruction. And then actually, if we just know the OP code field, then we can select, we can decide these control signals, right? You understand? Okay, so actually it's not difficult, right? So if we just understand how instructions are executed, or how instructions operate in a processor, then actually we can define control signals based on the operation of an instruction. Okay. Then how about the load instruction? Load word x1 and immediate x2. Okay. So this is also OP code. Okay, and then if the OP code is 0000011, then we can say that, oh, this is the load instruction, right? Okay, so this is the load instruction. How about the branch? The branch is obviously 0, so this is not a branch instruction. How about the map read? So you know, this is the load instruction, so which means that the data is read from data memory, obviously. So memory read is 1. Right, because we need to read data from memory. How about the map to read? So the data is read via this memory port, read via port of the data memory, right? So actually this path needs to be activated. Okay, so we need to store data from data memory, right? Here, so it should be 1, right? Because this path is selected, right? How about so ALU later? Mem right? This is the load instruction. So data is read, data is not written. So obviously 0. ALU source. How about the ALU source? This is the address, and the address is generated by ALU, but how? X2 plus immediate. So for the archive instruction, actually for the archive instruction, this data is register data. But for the load instruction, actually, the one of operand is immediate number, right? So where is the immediate? Immediate number is generated by immediate generator. And then for this box multiplexer, so we need to select this input, right? So ALU source is 1. Well, it's not difficult, right? And then how about the red line? It's 1 because load word has RD. Right. So we can define control signals like this. And then if we use the store word, okay, if we use the store word, so how about the store word? So I will erase this one. Okay, how about the store word? It's like the store word RS2 and then immediate RS1. Okay, so this is the store instruction. The branch is 0, obviously mem read is 1 because store instruction. So we need to write data to the data memory. And then how about the mem to read? So store word actually store words does not have destination register. Okay, right. So actually we can set this value as 1 or 0. Any value is okay, right? Because actually the regular write is 0 because store word does not have RD, destination register. So data is not written to the register file, right? So because regular write is 0, this write data is not used, okay? So actually, so which means that mem to reg is don't care. So x, it can be 1 or it can be 0. Any value is okay. So it is called don't care. So it's x actually. Because this port is not used. And then reg write is 0 because there is no RD in store. ALUP, so I will explain later. Mem write is 1, right? Because the data is written to the data memory. And how about the ALU source? It says store word require immediate number as one of input operand, right? So we need to use the immediate number. So it is 1. Then how about the RS2? The RS2 is actually connected to the right data port. Okay? So RS2 is here. RS2 is, as you can see, RS2 is connected to the right data. Okay? So which means that this data is written to the memory. So this is the store word instruction. So we can also define the control signals of store word. Now, finally, PQ, the branch instruction. So PQ, X1, X2, and target immediate. So we already know the operation of PQ. So PQ reads two input operands from register file. And then we use ALU for comparing these two input operands, right? And then based on the result, then the PC can be PC plus immediate if the condition is true, or PC can be PC plus 4 if the condition is false. Right. So this is the operation of branch instruction, the PQ. So the mem needed is 0, mem to mem is done here actually, because branch instruction just update the PC. The read write is also 0. AAU source, how about the AAU source? So actually, branch instruction use read data 1 and RS out and RS1 out and RS2 out. So which means that the input operand from register file. So AAU source needs to, so we need to activate this port and this path and this path. So ALU source is 0. Why? Because ALU is given two operands from register file. Mem write is 0 because memory is not used. So we will learn about the ALU later. Then, how about the branch? The branch is obviously 1 because this is the branch instruction, right? Then, what is the operation? So if this branch is 1, so you can find the AND gate here. So one of AND gate is the one of input of this AND gate becomes 1, right? So it means the output of this AND gate is determined by 0. Right? So if the 0 is 1, then it becomes 1, right? Because this is the AND gate. 1 and 1 equal 1. And then if the 0 is 0, so it means that the result is not 0, then it becomes 0. So because 1 and 0 equals 0. So what does that mean? So this is the PQ, then two operands are just compared. And if the two operands are identical, it's the same, then 0 becomes 1. Because for the BQ, this ALU performs RS1 minus RS2. Okay? We now check the equality. So if the 0 is 1, then it becomes 1, then this path is selected. So it means that it should true. The condition of a branch is true, right? So, this is the PC, and then this is the immediate. So you can know that this is the PC plus immediate. So for the next PC plus immediate is updated to the program counter. Right, so this is the operation of the branch instruction, and then if we just set branch equal 0, then if we just set other control signals for branch instruction, then the branch instruction works like this one. So if the condition is false, so it means that 0 is 0 because RS1 and minus RS2 is not 0. So it becomes 0, then the output of this AND gate becomes 0. So this is false. Okay? The condition of branch is false. So this path is selected, right? That's what is this path. So this is the PC, and this is the PC plus 4, because 4 add instruction. So actually, the next PC becomes the PC plus 4. Okay? So this is the branch instruction. Okay? So if you understand, the exact operation of each instruction, actually we can set the control signals based on the required operations. Okay. Okay, then let's learn about the ALU control signal. So I mentioned that the ALU is the ALU performs the Y equal F A, B, and then A, B are two input there, and then we can define the function of ALU using ALU control signal. Then Y is the output of the ALU. So in the textbook, so we assume that this RISC-V supports load word, store word, and then add, sub, and, or, and BQ, right? So this load word and store word instruction, load word and store word instruction perform RS1 plus immediate, right? RS1 plus immediate. So add instruction isn't required because it's a RS1 plus immediate becomes the address. So actually, it means the function of ALU needs to be add. How about the branch? Branch is we just support BQ, which means that RS1. So we just perform RS1 minus RS2. So this is the subtraction. So the function of ALU is subtract. And then for the other R-type instruction, like add, sub, and or, it depends on the function of the R-type instruction. So actually the ALU, the actual ALU of RISC-V supports the many other instructions, but in this textbook we assume that this RISC-V processor supports only these instructions. So the ALU just supports these 4 functions. But the actual RISC-V ALU needs to support many other functions. So that's why ALU control signal is the 4-bit signal. So so actually in this table, the ALU supports only the 4 operations. So which means that we just require 2-bit control signal, right? But actual ALU, so the ALU actually supports many other functions. So that's why the ALU control signal is 4-bit signal. Okay. So, and then if you see that this full data and then complete the single cycle RISC-V processor, And you can find that this is the main control signal, and then the ALU control signal. And then the main control unit generates the ALU OP signal. And then ALU OP signal is given to the ALU control signal here, and the ALU control unit receive another part of instruction, right? So it is because, so actually this main control signal receive the OP code field. Okay, so based on the OP code field, we firstly generate the 2-bit ALU OP signal, right? And then based on the ALU OP, and then other instruction bits. So actually this is the func 7, and then func 3 OP 3 field of the instruction. Okay, so this main control signal, main control unit receives just OP code field. Then based on the OP code field, it generates the ALU OP, and then using the ALU OP and then other function field, then we can generate the ALU control signal. Okay, so this is the two-step control. So we can define the required operation of the ALU at this table. So as you can see, you can find the ALU OP here. So I mentioned that the ALU OP control signal is determined by OP code. Okay. And then, so actually load word and the store word have different OP code. Okay, so like the 00011, 01, 00011. But we already know that load word and store word actually require same add operation for ALU. So that's why the ALU OP is the same for load word and store word instruction. Then how about the BQ? The branch instruction, actually BQ and then other instruction like PNT and then PGE and PNE, same. So actually for this branch instruction, we require operation like the RS1 minus RS2, right? So if this is 0, then it's the PQ. And if we just check this is not 0, then it's the B and E, right? And then if this is less than 0, this is BLT, right? And then it's 0, greater than 0 or equal to 0, and this is the BGE, right? Understand? So actually, the RISC-V has 4 different branch instructions, and then actually for the branch instruction, and all branch instructions require double track operation. RS1 minus RS2. So then open code field is the same for all branch instructions. Then ALUOP is set as the 01. So this is the start. This is the end. And for the arithmetic R-type instruction, the OP code field is the 0110011, right? So you can find this field and this one. So here. So this is the R-type arithmetic. And then the function of ALU is determined by the different instruction like and, sub, and, or also exclusive, or some other instruction here. So actually for these R-type instructions, so R-type instructions require various functions from ALU. So in this case, we set the ALU code is 10, and then in this case, the real function of the ALU is determined by func7 and func3. Okay, so this table explains the behavior of ALU. So you can design the ALU based on this table. But actually, for the lab 4, so actually in the design name, our RISC-V processor needs to support more instructions. So actually means that you need to design the ALU of lab 4 based on this table, not the table in the text. Okay, so you need to design the ALU based on this table. Okay. Okay. So ALU is defined, and then we just define the ALU OP and then ALU control signal. So based on the demanded function of ALU. Okay. So this is the complete single cycle RISC-V. Okay. So you need to remember that we just understand how the instructions are executed, right? And then based on the required operation, then we just define data path elements. Okay? So we define some required steps. So like the instruction fetch, decoding, or register read, ALU execution, then memory access, and then register write based on the instruction, and then we define each data path element, right? And then the data path elements are connected each other. Okay, so this is the data path is complete. Then we define control signals. Then we define control unit. Then control signals are generated. So control signals are connected from control unit. And then it's done. The single cycle RISC-V processor is complete. Okay. So this is the hardware structure of the very simple single cycle processor. Okay. So using this single cycle processor, then we can design the CPU that can execute the RISC-V instructions. It's easy, right? And what's the problem? So I said that this is the simple, right? The problem is performance. Right. So in the single cycle processor, within one clock period, so this is the clock period. So this is the clock signal, and then within one clock signal, the required operations need to be complete, right? And then in the previous class, I explained that this is some execution model of the digital system. So this D flip-flop, this is D flip-flop, and this is the combinational logic. And then actually the TC, the clock period of this digital logic needs to be, the clock period needs to be greater than sum of delta T, delay. Okay. So it's a single cycle processor. So which means that the operation of each instruction needs to be complete within the single clock period. So TC. So TC is need to be greater than the sum of delays of the data path elements. Right. Then what's the problem? When the instruction is executed, then we need to use every data path element. Okay. So which means, for example, so as you can see, the load instruction is actually require every data path element. Okay. So actually for the load instruction, we need to fetch load instruction from instruction memory, and then we need to read operands from the register file, and then ALU is required. Then also we need to access data memory, and then the result needs to be written to the register file. So these are actually all delays: delta T, delta T, delta T, delta T. The delay is different: delta T1, delta T2, delta T3, delta T4, delta T5. Okay, so which means TC, the clock period, needs to be greater than delta T1 plus delta T2. So actually the summation of delta Tn. Okay. So if the clock period is increased, then execution time is proportional to clock period, right? So execution time is increased. So everyone wants a fast computer, but in this case, the TC is very long. The clock period is very long, so performance will be low. So that's the problem. So it's a very simple process architecture. So which means that we can understand it easily. But problem is PC is greater than the sum of delays of all data path elements. So PC is large. Then execution time is proportional to TC. Performance is low. We cannot use this CPU because it's very, very slow. If everyone wants to use a fastest computer. Okay, so we need to improve the performance. So we can improve the performance of the processor using pipeline. Okay, so it's done here. Okay. So this is the end of the single cycle processor. Then the next class we will learn about the pipeline. Okay. So actually, I plan to record the lecture because we missed the one class in the October. So I will record the lecture, and then I will post I will upload the lecture video during the weekend. So, and then in this lecture, I will explain about the pipeline. So please watch the lecture during the weekend. Okay. 감사합니다.